A volcano on Russia's. Kamchatka Peninsula has just hurled volcanic debris roughly 39,000 feet into the sky. Within hours, the resulting ash plume was racing east across the North Pacific at about 92 Erupts, heading straight for North American air routes. This isn't a one-off. Shiveluch has now unleashed major explosions, each sending material 10 to 12 kilometers high on July the 2nd, July 5th, July 9th, and July 20th. That kind of spacing a significant blast every few days tells volcanologists something specific about what's brewing beneath the mountain. If you want to keep up with how this develops, consider subscribing. Because what's happening at Shiveluch involves a volcanic process far riskier than a typical eruption. And if it worsens, the consequences will extend well beyond Kamchatka. When most people picture an eruption, they imagine lava spilling from an open crater. Shiveluch doesn't work that way. Its magma is unusually thick, closer to scalding tar than the free-flowing rock of a Hawaiian-style eruption. Because it can't flow out easily, it creeps upward and piles up over the vent, cooling and hardening into a lava dome. That dome keeps growing as fresh magma pushes up from underneath, adding bulk, while the outer shell hardens into a steep, fractured mound. But it's far from a stable structure. It's essentially a heap of partially cooled, badly fractured rock sitting on top of a vent under constant pressure from hot gas and magma. The inside stays scorching hot and gas-charged. Even while the outside looks solid, cracks form. Chunks break off in small collapses, send hot rock avalanching down the slopes. Even these partial failures can trigger explosions and ash plumes, since suddenly relieving pressure on the debris causes trapped magma to fragment violently. But the scenario volcanologists really watch for on dome-building volcanoes like this one isn't a partial collapse, it's total dome failure. If a large chunk of the dome gives way all at once, it strips away the material that had been containing the pressurized magma and gas beneath it, triggering an almost instantaneous violent decompression. The result is effectively a massive explosion powered both by the eruption itself and by the sudden release of all that pent-up pressure combined with the collapsing dome material. That's what generates pyroclastic flows, blistering avalanches of gas ash and rock fragments that can tear down the mountainside faster than highway speeds, hot enough to torch vegetation and destroy anything in their way. Past pyroclastic flows from major dome collapses at Shiveluch have traveled more than 20 kilometers from the summit, far too fast to outrun. This is essentially what happened in 2023 when the volcano's strongest blast sent ash to roughly 52,000 feet, about 15.8 kilometers. Then, at a tipping point that instruments picked up, but the outside world barely saw coming. A major section of the dome gave way, triggering the decompression event that sent material to 52,000 feet, along with pyroclastic flows down the slopes. The current activity shows some resemblance to that lead-up. July 20th's explosion reached about 39,000 feet. July 5th hit roughly 39 to 400 feet. July 2nd sent material to about 36,100 feet. These aren't isolated blasts, weeks apart. They're recurring events within a sustained stretch of heightened activity with major explosions every few days this month. To volcanologists, this pattern signals that pressure keeps building and releasing inside the system. Fresh magma continues rising from depth. The dome keeps growing, and each explosive event either helps relieve pressure and stabilize the dome or gradually undermines its structure, stripping support from its base and pushing it closer to a major failure, like 2023's. Surface observations alone can't settle, which is happening. A 12-kilometer eruption column confirms a powerful blast occurred, but it doesn't reveal how much of the dome has shifted, whether magma is rising faster than before, or whether internal fractures are spreading toward collapse. Answering those questions would require seismic data on cracking and movement inside the dome, deformation, measurements tracking shape changes consistent with growing instability, and gas flux readings, showing whether emissions are accelerating. All of these monitoring methods face real limits at Shiveluch, a remote volcano in a region known for harsh weather and difficult access. Weather is adding another layer of difficulty. When the July 20th eruption was first detected, aviation alerts initially labeled it a possible rather than confirmed eruption because thick cloud cover hid the summit. It took roughly 2 hours before Himawari 9 satellite imagery clearly showed material spreading from the volcano and confirmed the event 2 hours during which ash was entering the atmosphere, but ground and satellite monitoring couldn't fully characterize it. Now a cyclone is approaching Kamchatka, bringing its own hazards. The storm didn't cause the eruption. There's no mechanism linking an approaching weather system to volcanic activity, but it can worsen conditions afterward. Strong cyclonic winds could accelerate and redirect the ash cloud, pushing it more forcefully toward North American airspace than its current eastward drift. Storm clouds could also blind satellites to the volcano at precisely the moment continuous tracking matters most. Then there's the rain. Heavy rainfall on slopes blanketed with loose ash, pyroclastic debris, and broken lava can rapidly mobilize that material into lahars, fast-moving rivers of volcanic mud and rock, with a consistency close to wet concrete destructive. Through sheer speed, mass, and abrasiveness, lahars don't need a fresh eruption to form, they just need loose debris on steep slopes and enough water to saturate it. All three conditions are converging at Shiveluch. Right now, lahars have historically ranked among the deadliest volcanic hazards worldwide, partly because they travel far down river valleys, reaching communities with no direct view of the volcano. The 1985 Nevado del Ruiz disaster in Colombia, where lahars, triggered by melting summit, ice killed more than 2,000 people, remains one of the starkest warnings in volcanic history. At Shiveluch, this particular lahar risk is mostly confined to Kamchatka and doesn't extend to North Pacific flight paths or North American land, but it's a serious immediate threat to anyone in the surrounding valleys. Now to the piece that reaches far beyond Kamchatka. The ash cloud from the July 20th eruption was clocked, moving east-southeast at around 148 km, 92 in pH at altitude. By the time aviation monitors were discussing it, the leading edge was already hundreds of kilometers away, crossing from the Tokyo Volcanic Ash Advisory Center zone into the Anchorage Center's territory, which covers the flight corridors, linking Asia, Alaska, and North America. Volcanic ash is a serious aviation hazard and a different beast entirely from the wildfire smoke that's affected parts of North America this summer. Wildfire smoke is soft carbon, particulate, largely harmless to jet engines. At flight altitude, volcanic ash is made of hard, jagged fragments of rock and glass formed when magma shatters explosively. Inside a jet, engines heat. Those particles melt, then resolidify on cooler turbine components, degrading performance or causing total engine failure. Ash also abrades windshields, reducing visibility, and can foul sensors and ventilation systems. The 1982 incident, in which a British Airways 747 lost all 4 engines flying through ash from Indonesia's Gelunggung volcano, before the crew managed a restart during a harrowing descent, remains the textbook example of what ash can do to an aircraft. The tricky part is that ash clouds aren't always visible, especially at night, or when mixed into ordinary-looking clouds. And standard aircraft, weather radar doesn't reliably detect ash the way it detects precipitation. That's why the International Volcanic Ash Advisory System exists, why Anchorage and Tokyo issue continuous updates, and why airlines reroute around known ash hazards even when conditions look clear. Right now, aviation advisories are active for the affected North Pacific airspace. The key question for Canadian airspace, especially the busy transcontinental and trans-Pacific routes through Vancouver, is whether the ash will reach concentrations high enough to force rerouting at cruising altitude as it crosses the Pacific. During 2023's eruption, ash did reach Canada's west coast, prompting Transport Canada and NAV Canada to implement monitoring procedures with some carriers, rerouting eastbound trans-Pacific flights from Vancouver. Effects that time were limited, but it proved a major Shiveluch eruption can send enough material at sufficient altitude to affect aviation clear across the Pacific. So far, the current sequence hasn't matched 2023's scale. There's no confirmation of another catastrophic dome collapse. The ash columns reaching 10-12 kilometers appear to be coming from repeated explosive venting, typical of this active phase. Not a major dome failure. That distinction matters a lot for aviation risk. A full dome collapse would inject far more material higher up over a longer period, meaning a larger affected airspace and a longer-lasting hazard. That threshold hadn't been crossed yet, but the monitoring gaps from cloud cover and the incoming cyclone leave real uncertainty about whether the dome is trending toward or away from that point. For now, ash advisory centers are actively tracking the cloud, issuing updates as satellite data comes in and coordinating with aviation authorities across the region. Airlines have what they need to make rerouting calls, and Canadian authorities are monitoring through the same international coordination channels refined during the 2023 event. On the ground in Kamchatka, the combination of ongoing eruptions and the approaching storm means an elevated hazard period, requiring close local monitoring in the days ahead. The ash cloud is still crossing the Pacific, the dome is still evolving, the cyclone is still approaching. Updates will follow as new information comes in from the Anchorage Volcanic Ash Advisory Center, satellite monitoring, and the scientists tracking one of the most persistently active and structurally hazardous volcanoes in the Kamchatka Arc. To understand why this volcano behaves the way it does, it helps to understand Kamchatka itself. This narrow Russian peninsula bordered by the Pacific Ocean and the Sea of Okhotsk sits directly above a subduction zone where the Pacific Plate dives beneath the North American Plate at roughly 7,500 millimeters per year, among the fastest convergence rates on Earth, that feeds intense volcanism along the entire peninsula, which hosts more than 30 active volcanoes, and some of the most frequently erupting systems in the northern Ring of Fire Shiveluch alone has produced at least 60 major eruptions in the last 10,000 years. What sets it apart is its magma chemistry, among the highest silica content of any Kamchatkan volcano, placing it in the andesitic-todesitic category. High silica. Magma is thick and resistant to flow when it traps dissolved gas rather than letting it escape gradually. The core reason dome-building volcanoes like this one are so hazardous compared with low silica systems. Basaltic magmas flow easily and vent gas, steadily producing the gentle lava flows typical of Hawaiian volcanism. High silica magmas bottle up gas under pressure until it finds a violent way out. Shiveluch's dome-building cycle has run continuously since at least 1980, growing partially, collapsing, regrowing, and occasionally suffering major failures that reset the whole process. The 2023 collapse was the most significant in recent decades, destroying most of the existing dome and carving out a new crater about 1 kilometer wide. Since then, fresh magma has been rebuilding a new dome inside that crater. Early on the crater walls offer some structural support, but as the dome grows past the rim, that containment disappears, leaving the structure increasingly exposed to flank collapse. This month's repeated explosions suggest the dome has reached an advanced enough stage to generate the kind of gas-driven explosive activity typical of Shiveluch's more dangerous phases. Whether frequent explosions ultimately stabilize or destabilize the dome is genuinely debated. Some volcanologists see them as a pressure release valve, letting the system vent gas before reaching a catastrophic threshold. Others see them as slowly fracturing and weakening the dome stripping support and paving the way for future collapse. Shiveluch's history shows both patterns, so the current explosive sequence can't be confidently labeled either way without better monitoring data than cloud cover and distance. Currently allow major collapses here also produce debris avalanches alongside pyroclastic flows. The failing dome doesn't slide down as one mass, but disintegrates into a fast-moving chaotic mix of blocks and fine debris driven by gravity and the explosive pressure release. Past major collapses have buried large stretches of the caldera and rerouted drainage, Kamchatkas. Geological record even shows prehistoric Shiveluch collapses far larger than anything seen in the modern monitoring era. A reminder that this volcano's potential exceeds anything witnessed in recent centuries. On the Volcanic Explosivity Index, a logarithmic 0.8 scale, Shiveluch's largest historical eruptions rank around 5 to 6, comparable to Mount St. Helens in 1980, VEI 5 in the 1991 Pinatubo eruption in the Philippines, VEI 6, which cooled global temperatures for 2 years by injecting sulfur dioxide into the stratosphere. The current sequence sits at the lower end of that range, significant but not yet approaching 2023's scale, or Shiveluch's largest prehistoric eruptions. For aviation, eruption column height is critical. Taller columns push material higher, where upper-level winds can carry it much farther before it settles. Material, reaching the stratosphere above roughly 1,215 kilometers, can stay aloft for months and circle the globe, as Pinatubo demonstrated in 1991. Shiveluch's current explosions are reaching the upper troposphere and possibly the lower stratosphere at their peaks, right where North Pacific jet stream winds operate, and where volcanic material disperses across the ocean. Fastest winds during the July 20th eruption pushed the ash eastward at nearly 150 km/h, and within hours, the leading edge was already hundreds of kilometers southeast of Kamchatka, heading toward the great circle routes that connect Asia to North America over Alaska and the Aleutian Islands, some of the busiest long-haul corridors in the world, linking hubs like Tokyo, Seoul, Beijing, Shanghai, and Hong Kong to New York, Los Angeles, Chicago, and Vancouver. The 1982 British Airways incident was no one-off either. In 1989, a KLM 747 flew into ash from Alaska's Redoubt volcano and suffered a 4-engine failure before restarting them, a close-to-home example of exactly the kind of hazard Kamchatkan ash poses to the same Alaskan airspace. That history is why the Anchorage Volcanic Ash Advisory Center exists at all, monitoring the whole North Pacific and issuing warnings driven by the frequency of ash events from both Alaskan and Kamchatkan volcanoes. Avoiding ash isn't as simple as steering around a visible cloud. Trans-Pacific routes are optimized for fuel efficiency using jet stream winds, so detouring costs time fuel and money decisions. Airlines base on ash position and concentration forecasts from the advisory centers, built from satellite data dispersion models and pilot reports. The system works well when a cloud is clearly defined, but struggles when ash spreads thin over large areas or cloud cover blocks. Satellite tracking. Exactly the situation at Shiveluch right now. For Vancouver, a major hub for domestic and international trans-Pacific traffic flying directly into the airspace, Kamchatka ash can reach the concern is familiar from 2023, when Transport Canada and NAV Canada coordinated with the International Volcanic Ash Network and adjusted some flight paths. Effects were limited that time because the cloud had dispersed enough by the time it reached Canada, staying below thresholds requiring mandatory rerouting. Whether the current cloud has similar or larger effects depends on how the eruption evolves and whether more major explosions add material over coming days. There's no confirmation yet of a catastrophic dome collapse. The current activity is being treated as a continuation of this month's elevated explosive phase, rather than a shift into something more dangerous, but monitoring gaps from cloud cover in the incoming cyclone mean the situation demands close attention. A sudden jump in eruption intensity, more frequent explosions, or signs of major structural change in the dome would all point toward escalating hazard. What's certain is that Shiveluch's current eruptive episode isn't over. This month's pattern points to an actively pressurized system with fresh magma still arriving from depth. The dome keeps evolving. Monitoring teams are watching as closely as weather allows, and aviation authorities across the North Pacific are tracking the ash cloud as it heads toward North American airspace. For now, this is a situation calling for elevated attention rather than immediate emergency in North America. But given what's unfolding on the other side of the Pacific, that elevated attention is exactly warranted. One more angle ties this event to the broader story of North Pacific volcanic risk, one that affects millions of people who'll never hear. This volcano's name, roughly 300 commercial flights. Cross the North Pacific daily on Great Circle routes between Asia and North America, and most passengers have no idea their route passes near some of the world's most active volcanoes. The Aleutian Islands, stretching from Alaska toward Kamchatka, sit on the same subduction zone that feeds Shiveluch and volcanoes there. Cleveland, Pavlov, Bogoslav, Veniaminov, and others have forced flight path changes multiple times in the past decade. Shiveluch adds the Russian side of that same volcanic aviation corridor. Monitoring has steadily improved, combining geostationary and polar orbiting satellite imagery with atmospheric dispersion models that project ash cloud movement from wind data at various altitudes. Advisories and significant meteorological notices go automatically to airlines and aviation authorities, reaching pilots during flight briefings and via in-flight data links. It's a far cry from 1982, when the British Airways crew had no warning at all, but perfect detection still is possible, especially when cloud cover hides the source or ash spreads thin at cruising altitude. That gap between what satellites can confirm and what's actually in the atmosphere is a permanent limitation that better technology can shrink but never fully close. If the current Shiveluch situation makes anything clear, it's that volcanic hazards don't respect borders or oceans, they cross them.